I know everyone is always very busy. And so today we have another presentation in our series from Characterization at UBC. The session will be recorded and then later made available on our YouTube channel. And I also would, if you haven't done so yet, encourage you to subscribe to our mailing list. And you can find the QR code for this here, or otherwise also the link on our UBC and Characterization page. And likewise also the link to the YouTube channel in case you want to watch any of the previous events in this series. So today we welcome Dr. Matt Tarling. He is an assistant professor in the Earth, Ocean, and Atmospheric Sciences Department at UBC. He did his undergrad at McGill and then his PhD at the University of Otago in New Zealand, and then returned for a postdoc at McGill, and we were lucky to have him join our department. And he will talk today about how reactive mineral growth and deformation create one of nature's toughest materials, nephrite jade. And with that,
thank you, Annette.
Thank you.
Thanks. Right. So before I launch into the talk, I'd like to introduce myself specifically for the mineral characterization crowd that I might not necessarily overlap with too much. I am a field geoscientist, and I study deformation processes in the Earth. And I do that typically by telling narratives that start by looking at some kind of geophysical phenomena and examining it by going into the field, examining outcrops and rocks that might record information about it, applying a field to micro-nanoscale analysis. So that's where my characterization background comes in. And ultimately, a lot of what I do is the characterization of deformed materials. In this talk, I'm actually going to take a different approach and really lean into that characterization and focus on the material itself, and we'll build up the story from there, which is on nephrite jade. So you've likely heard of the term jade. Perhaps you've not heard of nephrites, or maybe you've heard of nephrite and jadeite jade. They're sort of two different types of jade. Jade itself is not actually necessarily a geological term. It's more of a cultural gemological term, but it refers to these two types of jade, one being jadeite. This is a rock made up of pyroxene. It's an attractive rock that's often carved for jewelry and ornamental objects. And then there's nephrite, the subject of this talk, which is also this rock that's carved. And that's sort of where the two are tied together. They both have an attractive greenish appearance, and so they've been lumped together in the jades. But we'll be focusing on nephrite jade, which is...
We still need to share the talk.
Oh, right.
It doesn't show up on the video. So.
Okay, thank you. How about this? Does that work? Okay. Well, sorry for anyone that was missing the visuals there, but we're back into it, and we're back into nephrite jade here. And so I think any good talk should start with some kind of motivation. Why should you care? And that sort of depends on the lens that you're looking at things. One might be cultural. Nephrite jade has this very important cultural importance across different cultures. In Aotearoa, New Zealand, it's important to the Maori. It's important in Chinese jade traditions for tools. Art has an important component of identity. And this really originates from the fact that wherever you find nephrite at the surface of the Earth, in the Paleolithic times, it was used as a tool. And that's a pretty universal rule around the world. And we'll see that's because of its exceptional properties. And so this has sort of translated over time into cultural importance in some places. And this ties into one of its physical properties. It is one of the toughest, I will say, silicate or inorganic natural materials on Earth. Has an exceptional fracture resistance, and we'll see that it comes not from the composition, but rather from the microstructure. My interest in it is that if you make this ultra tough material in the context of an earthquake generating fault, you can fundamentally alter that fault's property, the rheology of that fault, and that might have some significant implications. We won't really be touching too much on that, but that's really where my angle comes into studying this. Then finally, there's the idea of economic value. At one time in Canada, this might have been the case. Canada does host some of the largest nephrite deposits in the world. There's, however, very limited domestic demand. It's also been restricted. It's mining in BC. So probably not the greatest motivator in Canada, but that might not be true if you were a Chinese researcher studying Chinese nephrite jade deposits. So with that, I've sort of touched on this. What is nephrite? It is a monomineralic rock. It's entirely composed of the mineral, of this amphibole mineral, tremolite actinolite. This is a mineral series that we'll see in a moment. And the important part is it's entirely made of these acicular, that is needle-like to fibrous minerals, with a very dense, compact microstructure. This, and the other fun fact is it is British Columbia's official provincial gemstone, if you will. So this mineral constituent, this tremolite actinolite, it's a solid solution with the magnesium and iron being the end members of an amphibole mineral. It tends to grow in this prismatic form that you see here. And its structure is a double chain silicate that's made up of these two linked chains of silica tetrahedra. And that kind of is what gives rise to that fibrous habit. Now, before I forget, for every slide that has a little sort of rock symbol in the top corner, there is some corresponding geological sample. I haven't labeled them, so you can take the time to, during the talk, zone out, look at some rocks, pass them along, see if you can link them up to what's being seen. There's also a slide viewer that will allow you to see some of these structures at the hand sample scale. You simply hold it and twist the circular dial. So see if you can find some of the things that are presented in this talk as we go along. Don't worry about being disruptive and moving that around. So back to this tremolite actinolite amphibole. In terms of mechanical properties, this crystal by itself is kind of unremarkable. Its fracture toughness, that is the resistance to the propagation of a fracture, is sort of very normal, average. This is the value for essentially all silicate minerals. The fracture energy, the energy required to create new fracture surface, is also right on par with any other sort of rock-forming silicate within the Earth. And so, like I mentioned before, it's in fact the microstructure that makes the difference. So here we have a lump of nephrite jade. If we zoom in, we obviously don't see very much, but if we use something like an electron microscope, here we're looking at a secondary electron, scanning electron microscope image, and we can begin to see what it is that gives rise to that incredible toughness that we'll be looking at in a moment. Here we can see those individual amphibole needles, and if you look closely, they've all got sort of variable orientations. They are all sort of tightly packed. They come in clusters where within a single group, they might be well oriented, but you can see a range of orientations present throughout. And so if you imagine a fracture that has to propagate through this, if it's propagating along grain boundaries, it's not going to go very far until it hits another mineral and have to deflect. And in fact, it's this fibrous nature that makes it so incredibly strong. So when we look at the mechanical properties, fracture toughness is significantly higher than any single mineral grain, and the fracture energy is incredibly high. Now, by itself, these numbers might not mean a lot to you, but if we compare them to some common earth materials or some common engineered materials, for example, a granite, we're looking at 1 to almost 2 orders of magnitude in terms of that fracture energy. Greater for the nephrite. The nephrite's stronger than sort of standard alumina ceramics. It starts to be comparable to a very modern transformation toughened zirconia. For the geologists, this is a material that's crystallized in its metastable form as a ceramic. When a fracture propagates, it induces the phase transformation with a volume change that seals off that crack. So we're dealing with a natural material that sort of compares to some of our best, most advanced ceramics, kind of in line with cast iron in terms of toughness. And that really all comes down to the microstructures, to those fabrics. And it raises an interesting question. Could we leverage this kind of natural material, or at least the processes in which they form, to make stronger modern ceramics? We'll get to that eventually in the end, but this is ultimately the question we'll be addressing, is how do we make this nephrite jade? So the way we're going to approach this is we'll begin by just considering the simplest thing first, just the chemistry. We saw that it was a calcium, magnesium, silicate mineral, and so we're going to look at ways that we can make that tremolite actinolite to begin. So there are sort of 2 general ways we can do this. We can do this metamorphically or metasomatically. We'll see one by one what this means. In this metamorphic context, we take some assemblage of minerals and we bring them to a new set of pressure and temperature conditions under which the equilibrium stable assemblage includes new minerals. And so we get a mineral reaction that takes place governed by pressure and temperature, in which we can describe this in pressure and temperature space. I've selected one such of these mineral reactions where we're going from a carbonate mineral with silica, adding a bit of water, forming our tremolite, but we also form a carbonate in the mix. And so this is a little more complicated because we do have CO2, and so the partial pressure of CO2 comes into play, but the general idea is that we can find somewhere in PT space that we can grow our amphibole mineral. There's a problem with this for a few things. One is the resulting rock that forms is not just tremolite, it's whatever that equilibrium assemblage is. And the second, this equilibrium growth tends to favor really large crystals. So you can kind of recognize some elements of nephrite here. We have those acicular crystals, but they're centimeter scale, and they're in a rock with, in this case, a calcium carbonate. So probably not the right path. In metasomatism, we can form new minerals by using the chemical alteration of rock driven by infiltrating fluids, dissolving and reprecipitating minerals. And in this case, these reactions are really more driven by very strong chemical gradients, chemical potentials. And with the right system, in this case, we're looking at an activity diagram of calcium and silica. If we start with this mineral serpentine, we add some calcium and some silica, under the right conditions, we can end up with tremolite being the only stable mineral. And so this is very promising in terms of a mode to make our tremolite rock. This mechanism here, so starting with serpentine, add a bit of silica, add some calcium, and make our tremolite. So the first thing we need to do is get a hold of this mineral serpentine. Serpentine is a hydrous magnesium phyllosilicate, and it forms when you add water to the rock that makes up the bulk of the Earth's upper mantle, up in here in this Earth cross-section known as peridotite. So this is an anhydrous magnesium silicate. So we get a hold of some peridotite. In this case, we're going to add a bit of water, and we form our serpentine. So we have our first reaction, our first reactant for this formation of tremolite. Next up, we add to it some silica, some calcium, and we form tremolite. But again, we end up typically with fairly large crystals of tremolite. If you just let this reaction take place within the Earth, this is sort of the rock that you'll end up with. Again, you can recognize that prismatic acicular habit of that tremolite, but looking at it, those grains are way too big, and we can examine this in, here we're looking in cross-polarized light. So this is a photomicrograph in which we have a thin slice of rock, about 30 microns thick, placed between two polarizers. That initial polarized light, once it passes through these birefringent crystals, gets split into two orthogonal waves. That birefringence means that each wave experiences slightly different refractive indexes. They experience a retardation. Upon recombination in that top polarizer, we get these beautiful constructive interference colors. So it tells us a little bit about the orientation of the crystals relative to the polarization of light. And we'll see, we'll be seeing some similar things in other slides. But again, what we see here is that we're dealing with centimeter scale grains. So we've made a monomineralic tremolite rock, but it's not going to be especially strong. It's going to be no stronger than any individual grain. It's going to be fairly easy for fractures to propagate through this. So what are we missing? We're missing that structural and geological context. So we're going to go to the places where we do find nephrite forming in nature. And so in doing so, we're going to examine some context, some geological context. And these are geological faults. So these are large breaks in the Earth's crust along which two blocks move relative to one another, driven by plate tectonics. And the study sites we're going to be looking at are outcrops and specifically samples from ancient exhumed faults. So faults that were active deep in the Earth and that are now exhumed and accessible at the surface. And we're going to look at samples that represent sort of snapshots along the way to see if we can decipher some kind of pathways for formation for this unusual microstructure. So to give you a bit of context, we're going to examine one of these so-called field sites, these study sites, where we have these faults present at the surface in the Earth. And so we'll take a quick trip here. We're on campus, zipping around the world. So we're going to be looking at samples here from New Zealand, from California, from BC and Taiwan. But we're going to examine, just in this case, one of these field sites in New Zealand. So this is in the South Island of New Zealand. And right now we are flying over this fault, this geological fault that is bringing together material. On one side, we have this reddish rock. This is our serpentine. On the other side, we have this gray rock. This is the rock that's going to give us our calcium and our silica. And importantly, the region between them, that's our fault, that's the place where motion is accommodated, is this incredible messy mixing zone. So this whole saddle that you're looking at here is the expression of a fault where there's material from both sides that are being ground up and essentially intensely sheared together. And if we look at a cross-section of what that might look like, we can see that we have what we call a shear zone, a zone in which shear has been accommodated. And it's really a really intense mixing zone where components of either side of the serpentine and that calcium silica rock are being combined together. And this is where we can have these metasomatic reactions that will produce our nephrite. So we're adding our silica and our calcium. And one of the first things that we see, if we look for the incipient formation of our nephrite, are intense zones of veins of tremolite running through the serpentine. And so this happens typically at the contact between the serpentine and that calcic silicious rock. If we slice into this, we see really nice sharp boundaries between pieces of dark serpentine, where that pale greenish white is our tremolite, our nephritic tremolite. And you can imagine that if you removed all the veins in here, you might be able to sort of piece it together. This is what we call a breccia, a vein breccia, sometimes a crackle breccia or a puzzle breccia. And what we have here is extremely rapid precipitation of the minerals in those veins due to rapid opening. And it's this rapid precipitation that gives us our first element for forming our nephritic fabric. So if we take a closer look here, we see that we do indeed have some really fine needles. So we're looking at 50 micron scale. This is a secondary electrons scanning electron microscope image. And so we do have our needle-like habit. Now, if we look carefully at this, so right now we're going to look at an electron backscatter diffraction image here, a map of this. What we do see is that although we do have a very sort of fine-grained scale, needle-like habit, there is a very strong crystallographic preferred orientation in this vein context. So this image here is an inverse pole figure. This is the X direction. These colors tell you essentially how well-oriented a given crystal plane is within our tremolite to the X, the horizontal of this image. So if you see green, that means the 101 is well aligned to the X. Same applies to the 001 for the red, and the blue, the 111. And we'll reuse this scheme throughout. But what we get from this is that we have a very strong preferred crystallographic orientation where our tremolite crystals are subperpendicular vein margins. In the geological world, this is actually very common for any vein-forming context. The crystals grow often outward from the vein walls into empty space. However, in this context, the rapid growth during that opening and precipitation has given us our first element of sort of nephritic fabric, which is ultra-fine grain scale. And so this is sort of maybe our step one, our type 1 primary vein nephrite. Now you have to remember that we're in a shear zone, and in many cases, this won't have been the end of the road for this rock. Some of the samples that we see experience this and somehow came back to the surface without having undergone any further processes. But others in those faults and shear zones will have continued to experience deformation. And so we add the effects of deformation. Now we're looking at one of these veined rocks, but what you can recognize here is that our veins are all squiggly. They've all been deformed in some way. And so if we take a closer look, you can see that the deformation and the change in shape can be quite intense. You can imagine that these veins may have once been straight and that they've been squished and compacted together. And if we take a close look at what that looks like in terms of the fabric of those tremolite needles within it, what we see is that the tremolite needles are beginning to show signs of, well, deformation, the very deformation that has accommodated this sort of bending and folding of the veins. And they do so by the presence of interpenetrating grain boundaries. So that is to say that our individual tremolite needles, as we see in this EBSD map, are sort of penetrating into one another. And this is telling us an important clue about how this deformation took place. This is taking place through a process called pressure solution, where there is a very high stress, the material is dissolved, and it becomes reprecipitated somewhere where there is a lower stress. And if we look at the misorientation, the degrees of misorientation within a given crystal, that is to say, looking across a profile of the crystal, looking at how misoriented every single point is with respect to the overall crystallographic orientation within that grain, we see that we have kind of two classes of grains. Grains with very little misorientation, a couple of degrees, and these tend to be aligned to our folds. And then we also see grains with a high degree of misorientation, and these are the ones that are acting as indenters or penetrating into the other grains. Again, this is indicating to us that we are dealing with a deformation process. And while this is happening, we also have the growth of new tremolite grains that are forming within this. This kind of gives us our second step to the process, the folding of our veins. Now, if we allow this folding to continue to take place, grow new grains, and essentially replace all of the tremolite, perhaps through continued veining and mineral growth, eventually the rock will be entirely comprised of our tremolite, our nephritic-like fabric of tremolite. Now, we're not yet quite at a perfect, complexly interpenetrating fabric like we saw before. And in fact, under these conditions, if the stress state that results in this folding is sustained and continued, eventually, all of those grains will align themselves to a single orientation. So the grains will align themselves such that the long orientation is perpendicular to the overall compressive stress. And this, in geology, we refer to this rock as a schist. It has a foliation, and that foliation reflects that deformation. So if we continue to grow and deform under these sustained stress conditions, we're going to form a very well-aligned rock in which the tremolite have all their grains lined up within what we call a schistosity. We can have a closer look at this, of course, with the scanning electron microscope, and you can see that high degree of alignment of those tremolite grains. So in a way, we've actually taken a bit of a step backwards. We still have needle-like behavior, but we've kind of gained an alignment. However, it's worth noting that within these shear zones, the actual organization of stress is incredibly complex. And we might be looking at a single rock that's, the size of your hand, but stresses evolve over time within a larger region, and they do so in a complex pattern. And so even though this results in a very strong alignment, it might only be in a small pocket. And that stress field is liable to change. So despite this resulting in that super strong alignment of needles that we see here, that might not be the case if we continue to deform. And that's our next step. We take our foliated tremolite schist, some might call this a semi-nephrite, and we sustain deformation under new stress conditions, evolving stress conditions. So perhaps within that shear zone, things have shifted slightly, and there's a new dominant force. So in this case, we're going to imagine that we're going to compress our foliation at 90 degrees to that original orientation. And this is going to develop what we call a crenulation. The same process of grain reorganization by pressure solution is now going to take action, but with our compressive stress against the long axis of those needles. And so essentially that will end up folding and buckling our tremolite. Here we have a cross-polarized image that's sort of cycling through with rotations of the polarizer. And you can see that our layers are buckling, and this folding, which is pervasive and penetrative through the sample, is our crenulation. And if we allow this to progress under those sustained stress conditions, we can form these rather remarkable rocks which have what's known as a fully penetrative crenulation cleavage. So these lines here, we're looking at a cross-polarized image with a retardation wave plate giving us a 90-degree phase difference and a planes polarized light image. And we can see here that what this image is telling us is that we have a strong alignment of our nephrite needles, but in these fine bands. And these fine bands represent that same folding that we saw before, but taken to an extreme. So that folding has occurred all the way across here, and the axes of our fold are diagonal across this image. If that's difficult to imagine, let's look a little bit closer. So here we have those same images here, and if we look at the scanning electron image, it's a bit difficult here, it's a bit dim, but you can actually see these microfolds that are occurring across these domains. Crystallographically speaking, if we look at our EBSD maps, within a given domain, we have a very strong alignment, but now things are getting a little tight, things are getting compressed, and we actually have changes in crystal alignment that are occurring on quite a fine scale. So we're beginning to develop that nephritic fabric. This deformation is still favoring very small needles as needles reorganize and regrow through this deformation. And that crenulation is giving us different orientations. And so this gives us highly aligned tremolite needles kind of in folded domains throughout the rock. This gives us our third type. Now, if we sustain those conditions that are forming that crenulation, that are compressing it, eventually this is going to reorient itself fully and turn back into a schistose rock. So the schistosity will simply be vertical as all those needles compress and reorient themselves with that stress field. But again, this is a complex system where stresses at a local scale are subject to constant reorganization. And it's in fact this constant reorganization that we need in order to create this kind of chaotic fabric throughout the rock. And so this brings us to sort of our final condition, which is that deformation needs to frequently evolve in the stress field orientations. And so all nephrite that we examine, all this sort of high-grade nephrite jade, has what we call a domainal fabric. So if we examine the fabric of the nephrite, we can find elements of, for example, folds. Here we can see a hinge of a fold. If we look closely, we can also find hints of ancient crenulations that were preserved. These nodules and domains, these crenulations, all those previous fabrics, the schistose, the crenulated, the folded, have all been preserved in small domains. And the issue here is as I was going through this sort of scheme, you imagine the entire rock undergoing that transformation. But as I mentioned, stress fields are very heterogeneous within the shear zone and can even vary at a local scale. And there can be reasons for small domains to be preserved, stress shadows, pressure shadows as things evolve. And so ultimately, it's this constant changing of stress fields during deformation, during mineral growth, that favors this very complex mineral fabric. And so here we look at that EBSD map, and we can see that locally, there are domains that are well aligned, but globally, over the scale of, in this case, this is a 200 micron scale bar, we have such a range of orientations, and it's this range of orientations of these amphibole needles that gives us that incredible strength within the rock. And so this is really the final key, the final piece of the puzzle to developing our nephritic fabric that we saw earlier. We have this process where we begin with veins combined with mineral overgrowth. We fold those veins. We might move into some stable stress fields, stable shear zone kinematics, develop either crenulations, foliations. We could even switch between the two. But as stress fields change, as deformation conditions change slightly, ultimately we evolve towards this domainal nodular nephrite. Now, at any given point, we can sort of exit this highway and perhaps turn into a schistose nephrite or crenulated nephrite. And this condition of constant change is in fact why nephrite is relatively rare in the world. It's one of the reasons it's valued. Is in most shear zones, if you go and find some kind of nephritic tremolite, it's very liable to have sustained, or at least the rock that you see, the last thing that happened to it is sustain some kind of stable kinematics that turns it into a schist. So the vast majority of the world's nephrite is schistose, But under the right conditions, you get this domainal fabric, and that's ultimately what characterizes nephrite jade. So if we turn to this question, how do you make nephrite jade? It's this combination of metasomatically growing our tremolite while deformation is taking place, and those at least local stress conditions are continuously evolving. And this leaves us with that initial question is, well, could we use this knowledge as a template for making ultra tough modern materials? And it's at this point that we definitely leave my expertise. What I can say is in the 1970s, there was a great deal of interest in the mechanical properties and the microstructural properties of nephrite. That's where all of the information and the mechanical data that I have come from. So people were clearly interested, but at the same time, those reaction toughened ceramics were being evolved. And the reality is this is not a practical fabrication pathway that I've presented. It's not really that helpful industrially. Maybe it could be used in some way to inspire an industrial process. It certainly is an interesting template. If we look at ceramics, there are some equivalents that may be easier to do. So there are structurally, we have whisker or fiber reinforced ceramics that in many ways share a lot of microstructural similarities with silicon carbide whiskers or fibers within a ceramic matrix. And then, of course, for strength, we have sort of equivalents in terms of these transformation toughened ceramics. So where I rest on this question is perhaps not, though it has been a good 50 years since people have considered nephrite as a potential in terms of inspiration for creating modern ultra tough materials. So I'll end on that. We've got heaps of time for questions. Thank you.